Hello everyone. Let's take a look at limiting reactants, which is part of stoichiometry, also called limiting reagents. Up until now, you probably saw one on your homework, but we didn't have one in class, although we've kind of touched on it just a tad with a few examples that we have. But what I want to spend a little bit of time doing is talking to you about a limiting reactant problem. So one thing that's always fun to do is look at s'mores. So for those of you who don't know what a s'more is, that is this right here. So basically you have 2 graham crackers and 1 marshmallow if it's a big one. If you have smaller marshmallows, it's a little bit harder to do. But if you have a big marshmallow, you have 1. And if you have like a Hershey bar that breaks into like little squares, 2 chocolate squares is usually pretty good, maybe 3 or 4, but 2 is fine for our example. And so with those items you get together, you get a s'more. So what a limiting reactant problem is something where we come in and we talk about, okay, well, what happens if I have 24 graham crackers, and we'll just call it GC, and 13 marshmallows, which we'll call M, and we have 62 chocolate squares. So the question is, how many s'mores will I get? Okay, well, and I think most of you can probably do this very quickly in your head, but if it takes 2 graham crackers and I have 24 graham crackers, then that means I can get 12 s'mores from my graham crackers. If I have 13 marshmallows and I only need 1 of those, then that means I can get 13 s'mores from just that 1 marshmallow. And if I have 62 pieces of chocolate and I only need 2 to make my s'more, then that means I can get 31 s'mores from each one of those ingredients that make up the s'more. So the graham cracker, the marshmallow, and the chocolate. So when you're trying to answer this question of how many can I get, well, you can only make the smallest amount based upon the supplies that you have. So I can only make 12 s'mores. So 12 s'mores means that in this particular case, that the graham crackers are my limiting reactant or reagent, both words work. And these 2, I will have extras left over. I'm going to have extra marshmallows and extra chocolate. And because they're extras, we call them excess. They are in excess. And so that is what they are called, and basically what we are doing with limiting reactant problems. So just to kind of give you a couple more examples of like real world examples, let's take a look at another one. So this one, we're going to make hot dogs. So with this one, you have, the first thing is just the regular hot dog. Let's call it the meat to make it easier. And then you have the bun. And then we'll call this one the hot dog. And as you can see, we have something left over. Well, let's take a look. To make a hot dog, we need 1 piece of meat and 1 bun, and we will get 1 hot dog. We have 1, 2, 3, 4, 5. We have 5 of these, 4 of the buns, and that means since this is the smallest number, we can only make 4 hot dogs. We have 1 of the pieces of meat, the hot dog part that goes on the inside, actually left over. And so in this particular case, the bun is my limiting reactant. And then the actual meat part of the hot dog is my excess. And how much excess? Well, in this case, we detail that there's 1 left over. Sometimes you get asked how many are left over, sometimes you don't. So just be aware. All right, so here's another one for hamburgers. So for this one, we're going to have a bun plus cheese plus lettuce and plus a piece of meat, and we will get a hamburger. Okay, well, based upon the information that we have here in this particular equation, we need one bun, and we will use one piece of cheese. And it looks like there are 2 pieces of lettuce together, so we'll make 2 pieces of lettuce. And then 1 piece of meat to give us 1 hamburger. So with that being said, let's go count. We have 1, 2, 3, 4. We have 4 buns. We have 1, 2, 3, 4, 5, 6 pieces of cheese. We have 1, 2, 3, 4, 5, 6 pieces of lettuce. And we have 5 pieces of meat. All right, so the question is, how many hamburgers can I make? Well, don't jump to it. So let's just go through it really slowly, really quick. How are we figuring out this answer over here? What we're doing is we are taking the number that we have, so that was going to be 4, and we are dividing it by this number here, which is it's your coefficient. It's like your mole to mole ratio, basically, right? But we're not doing a mole to mole. We're just looking at it as the moles. So I need 1 mole of buns, or I need 1 bun. So 4 divided by 1 means I can get 4 hamburgers. Now I'll have to abbreviate it because it's a long word. I can get 4 hamburgers from just looking at how many buns that I have. Then, section that off so we can see it better. Then for the cheese, I have 6 pieces of cheese and I need 1 to make a hamburger. So I can make 6 hamburgers from my cheese. All right, now let's take a look at the lettuce. In this particular one, I have 6 pieces of lettuce, but I'm going to use 2 of those for every hamburger. So 6 divided by 2 is 3. That means I can make 3 hamburgers from the number of pieces of lettuce that I have. And then from the meat, I have 5 pieces of meat divided by 1, because that's its number, to give me a total of 5 hamburgers. Oops, I want to spell the whole thing. All right, so now we have to go through and take a look really quick at how many hamburgers we can make total. And I can get 4 from the bun. I can get 6 from the cheese. I can get 3 from the hamburgers. From the lettuce. I get 3 hamburgers from the lettuce. And I can get 5 hamburgers from the meat that I have. So with that being said, that means that my limiting reactant in this particular case is the lettuce. I can only make 3 hamburgers. That's it. Now, make sure that you are kind of keeping up with what we're doing, because we actually kind of have transitioned into doing some of the chemistry stuff that's associated with it. But it's really not that difficult when you're doing the chemistry work. So just if you get stuck or you get confused, just think back to something like s'mores or hot dogs or hamburgers or something that's easy. I will tell you that one big mistake that kids tend to make right off the bat is that they look at these numbers here. How many are you starting with? You're starting with 4 hamburger buns, 6 pieces of cheese, 6 pieces of lettuce, and 5 hamburgers, and they say, oh, that's the smallest number. 4 buns is the smallest number, so that's my limiting reactant, and the answer is no. So you have to make sure you're taking into account the number of each item that you are using, which is why we do this little math ratio here. So in this particular problem, our lettuce was the limiting reactant. All right, there we go. And then we have our bread, our cheese, and our meat, which are all 3 we have extra left over. And so those are the excess. All right. Then this is just pairing up cats and dogs, something that's not food. It's easy to do food because everybody likes that. But people like animals too. So we have a cat and we have a dog, and then we will have a pair of a cat / dog. So there'll be a partnership. So in this particular scenario, I have 4 cats and I have 6 dogs. So the question is, how many cat-dog pairs can I make? And the answer is going to be, really quickly, you guys know that the answer is 4. Because I need 1 cat for every 1 dog, and that will give me 1 cat-dog pair. So when I look at it that way, that means that cats are my limiting reactant, and that the dogs are my excess. So I have 4 cat / dogs that I make, and then there are 2 dogs left over. They aren't really doing anything. They're just left over. They don't have a partner. Okay, so now that we've gone through some examples that are not chemistry related, let's do something that is. Excuse me. Sorry, I have a sneeze. Okay, now let's look at this particular problem. Let's transition into chemistry. And it is no different. I promise you that it's not. So don't start trying to make it harder than it actually is. If we have hydrogen gas, plus nitrogen gas, and it yields nitrogen trihydride, also known as ammonia, not ammonium, ammonia. Okay, so as always, it's your favorite thing to do, I know. You got to write the chemical equation. We have hydrogen gas. So that's just hydrogen. It's elemental hydrogen. And that means I have to make sure that I remember that he's diatomic, so he gets a 2. Plus nitrogen gas. It's just nitrogen. He's a gas, his normal elemental nitrogen. So he's also one of the diatomic, so he also gets a 2. Gives me nitrogen trihydride. Now we're dealing with a compound, no longer an element. And nitrogen trihydride looks like that, also called ammonia. And then the next thing that you need to do, which is really important, is you have to balance it. So let's go ahead and do that really, really quick. If we take a look at this, remember, let's do hydrogen last, but you don't have to, but it might make it a little bit easier. On the left-hand side, I have 2 nitrogens, and on the right-hand side, I only have 1. And so that means I should put a 2, a coefficient of 2 right in the front. And when I put a coefficient of 2 in the front, there we go, I was trying to get different color. There we go, put a 2 right there. That gives me 2 nitrogens on both sides, and now it gives me 6 hydrogens on the right, because 2 times 3 is 6. So all I gotta do is put a 3 in front of H2. The number in front of nitrogen is not 0, it is a 1. You don't have to write the 1, but if you want to, because it helps you, that's fine. So let's double check really, really quick our math. So on H2, I have 3 times 2, which is 6 hydrogens. And on the right-hand side, I have 2 times 3, which is 6 hydrogens. And on the left-hand side, I have 1 times 2 nitrogens. And on the right-hand side, I have 2 times 1. So it is definitely balanced. Okay, so what is going to be a little bit different in this particular type of problem than what you have done in the past is one tiny little detail. And so we'll work a regular stoichiometry problem first, and then like that you have been working, and then I will throw in a slight change to let you, just so you can see what a limiting reactant problem is going to sound like, so you can handle it. All right, so you are given this problem and you are told that you have, let's say, 6 grams of hydrogen. gas. So you had 6 grams of hydrogen gas. And then the next question is, how many grams of ammonia will you get? That's your question. Okay. So this is just like a problem we've been working, and we now have our equation. It's written out and it's balanced. It's right here. So the next thing you need to do is list your known and your unknown. And remember, your known is the one that has the number. So I have 6 grams of hydrogen gas, which is H2. And how many, the minute you see that question word or that verb, that's your unknown. Unknown grams of ammonia. Okay, so I have my known and my unknown. My equation is written and it's balanced. The hard part is over. So just try and relax and think about this as being very systematic and going through it one step at a time. All right, so as always, and I've told you before, a lot of times, start with what you know. I know this. So I know that I have 6 grams of hydrogen gas. Great, that's lovely, but that's not what I want. I want to know how many grams of ammonia I have. So I have to multiply this by one of my conversion factors. And in my conversion factor, all I'm focusing on right now is I have to have grams of hydrogen. It's not highlighting very good on the dark. I have to have grams of hydrogen in my denominator here. That way it can cancel out. So even if I don't know which conversion factor to use first, I know this has to go here because algebraically I have to put it there so it can cancel. So look back at your list. You have a list with 4 conversion factors on there. And there's only one that has grams in it, and that is the molar mass. So we're going to go from grams. And then we're going to, actually I don't want to arrow. I'm going to do times the molar mass of hydrogen. Okay, well hydrogen's molar mass for one hydrogen is 1.01. So in this case I have 2, so it's 2.02 grams for every 1 mole of H2. And then when I do that, grams of H2 cancel out. Okay, there we go. Now I have moles of H2. I don't want moles of H2. I want to transition over to ammonia. So if you have the map, so the map that I gave you in class, we went from grams to moles, and now I need to cross over from hydrogen to ammonia. So I've got to cross over from moles to moles. So I'm going to have to use my mole to mole ratio. So here I'm going to have to use the mole to mole ratio. And I need my balanced chemical equation to do that. And I know, based upon my algebra, that if I have moles of H2 here, I have to have moles of H2 down here because they have to cancel out. So look back up at your balanced chemical equation up here, and I have 3 moles of H2. The coefficient is a 3. So I have 3 moles of H2 for every, now the question is, do I care about nitrogen or do I care about ammonia? Well, look at your unknown. Your unknown is ammonia, right? So that's the one I care about. I don't care about the N2 right now. It's got nothing to do with what I'm doing. So I have 2 moles of NH3. And when I do that, moles of H2 cancel out. And I'm left with moles of ammonia. And I'm halfway there because look, my unknown was grams of ammonia. So I've already gotten to the ammonia part, check. Now I need to get to the grams part because I have moles and I've got the wrong unit, but I've got the right compound, so I'm almost there. Now again, go back to the algebra. Let the algebra help you and guide you. I have moles of ammonia here. I don't want it. I want it to be grams of ammonia, so I know moles of ammonia has to go down here so it can cancel out. moles of ammonia. So I have to multiply this by a conversion factor. That's stoichiometry. All it is you start with what you know and you multiply it by a whole bunch of conversion factors until you finally get to your unknown. That's how it works. So I'll put a yield because that's where the actual yield is. So I need another conversion factor. I have ammonia. I have moles. Well, all those conversion factors have moles in them, right? So take a look at the units on your unknown, and it's going to be grams. And I need to go look and see on my formula sheet or on my my list of different types of conversion factors if I have something with grams of ammonia, and I sure do. It is going to be the molar mass, not of hydrogen like last time. This time it is ammonia. All right, so we know that all molar masses have 1 mole. I need to go calculate the molar mass of the NH3. So let's see, nitrogen is 14.01 and hydrogen is 1.01, but I have 3 of them, so 3.03. So 17.04. Okay, and then once I do that, moles of NH3 and moles of NH3 cancel out. Take a look at your units, because this is what I'm looking for. Match it back up with your unknown. And once you have made sure that it matches all the algebra, everything is canceled out that you don't want, you can't just make it disappear. You actually have to cancel it out properly, and it matches the unknown. Now you can do the math. All right, so let's take a look at what we've got. We are going to have 6 times 1, which is just 6, right? Times 2 times 17.04. All right, so my numerator is 204.48 grams of NH3 divided by 2.02, my denominator, times 3 times 1. 6.06. Notice there are no units left over in my denominator, so I'm not going to write them. So now let's do that division. Hmm, 33, my calculator says, remember we talked about what did your calculator say? 33.7293729.4. Whew, a lot. Now we know we're not going to turn in an answer like that. We have to look back at our sig figs. Our known is 6. So if I were really being smart, I would have done 6.0 to have 2 sig figs, but I didn't, so that's fine. This will help us review rounding. So look back at your known, and this known right here has 1 sig fig. Because we have to have 3 parts to our answer: a number with the proper number of sig figs, a unit, and the compound. Well, I need to write this with 1 sig fig, so it's actually good that I didn't put the 0.0 because some of you kind of messed this up on your quiz. That means that I have 1 sig fig right here, and I'm going to have to chop it off. Look back 1 space. Does this 3 here round the previous 3 up to a 4? The answer is no, it stays a 3. So it's a 3. However, think about this logically. Does 33 round to 3? And the answer is no. This first 3, the leading 3 right here, is in the tens place. And this second 3 is in the ones place. So this leading 3 is still has to be in the tens place. I can't change his place value. So that means I have to fill in a 0 until I get to where the decimal point would be. Although don't write the decimal point because that changes your sig figs. So 33.7 is just 30. No decimal point. Our units are here, and they're also left over in your problem. If you did it properly, you should have your units, they're there for you. Grams of NH3. All right, so with that being said, that's a regular stoichiometry problem that we have been doing. This is nothing new, this is review. Okay, so take a look at it. If you were struggling with that, maybe that helps, I hope. All right, so now what I'm going to do with this next problem is I'm going to come over here to the side, actually, so we can do a side-by-side comparison in just a second. All right, so I'm going to start with the question. We still are going to be using the hydrogen gas plus the nitrogen gas, so all that will stay the same. So what I'll do is just rewrite the equation. So I have 3 H2, I'll go back and add the coefficients. Okay, and that's a 1 and that is a 2. So the hydrogen gas and the nitrogen gas are reacting to produce the ammonia. All right, so what will be a little bit different about this one is I'm going to write out your problem. All right, so let's say we have 28 grams of nitrogen gas react with 2 grams of hydrogen gas. All right, so 28 grams of nitrogen gas react with 2 grams of hydrogen gas. How many? That's a Y. Grams of ammonia will you get? Okay, this problem over here on the left is a regular stoichiometry problem. The problem on the right is also a stoichiometry problem. However, what is different about it, it has a limiting reactant. And you're like, how do you know? You know you have a limiting reactant problem when you have more than one known. So if they give you information on your knowns and you have more than one, that's it. That's how you know. Because remember, when you see a number, that's a known. And they need to both be reactants in the chemical equation. So if I have 28 grams of nitrogen gas, that's a known. I have 2 grams of hydrogen gas, also a known. They're both reactants. This is a limiting reactant problem. So before I can go figure out how many total grams of ammonia gas I can create, I've got to figure out who's my limiting reactant. So just like up here, just like here, go up to the s'mores first. Just like when I was doing this one, I have to figure out how many, if I want to figure out how many s'mores I can make, I have to figure out which one of these, the graham crackers or the marshmallows or the chocolate, are going to limit how many s'mores I can actually get. So I'm doing the same thing as I was doing when we were talking about the food or the dogs and cats. It is the same. So just try and not make it too like scary in your brain, because I think that the kids get scared by it, but don't. It's the same thing. So I don't know how much ammonia I can get because I've got to figure out who, the nitrogen or the hydrogen, that's going to limit me. So how do we do that? All right, well, start out first of all, known and unknown, just like always. Well, I have 2 knowns, right? So write them both down. I have 28 grams of nitrogen and I have 2 grams of hydrogen, and my unknown is grams of ammonia. Okay, great. Well, remember when I told you that the stoichiometry, like with the s'mores or the hamburgers or the hot dogs, I said it's you're using your mole to mole ratio number. So we are using these numbers here, mole to mole. You're using your moles, which means I have to have moles, which in these I do not have moles, I have grams. So I need to go figure out my moles of each one of these really, really quick. So I can do my proper comparison. Okay, so what I'm going to do really, really quick down here at the bottom is rewrite my equation because I want to work with it while we're solving the problem. Okay, And then over here on the side, I am going to calculate my moles real fast. So if I have 28 grams of nitrogen, and I want to know how many moles of nitrogen that is, grams of nitrogen, oopsie, there we go, has to go in the denominator. 1 mole on top because I'm going to use my molar mass. One nitrogen is 14.01, so 2 nitrogens are going to be 28.02. So that is going to equal, it looks like how much? Let's calculate it exactly. I did times. I have to fix it. All right, so my calculator says 0.999286. So we're going to say that this is 1 mole of nitrogen. Because 0.992, yeah, that's going to be 1 mole. All right, then I'm going to switch colors so we can differentiate. I have 2 grams of hydrogen. I know grams of hydrogen has to go in the bottom so it can cancel out, just like I did with the nitrogen. I can do 1 mole of hydrogen in the numerator. That's going to be 2.02. That cancels out. And look, 2 divided by 2.02. Any wild guesses? It's also 1. It's 0.9900, which is 1. If you want to make it 0.99, that's fine. It's not going to change the outcome of our answer. All right, so I have moles. So for the limiting reactant, first thing you got to do is find your moles of each reactant. That's number 1. So that's the first thing you have to do is find the moles of each reactant. And then once you have that, then all you have to simply do is compare using the mole to mole. And you only have to do half of it. You're only really doing half of the mole to mole. So in case you're confused, let's take a look. Go back over here for just a second. The s'mores. I had my coefficients. I had 2, I had 1, I had 2, and I had 1. I was given 24 graham crackers. 24 divided by 2 was 12 s'mores. I had 13 marshmallows. 13 divided by 1 gives me 13 s'mores. I had 62 pieces of chocolate. 62 divided by 2 is 31 s'mores. So what you're doing is you're taking the moles, which are these numbers here, and dividing them by their own mole-to-mole ratio number. So I'm taking the graham cracker number of moles that I have and dividing it by its mole-to-mole ratio number. Not anybody else's number. It's got to keep it with that same reagent is what we would call it in chemistry. All right, so let's go back over to our problem and make sense of that. So right here, I've just figured out that I have 1 mole of hydrogen and 1 mole of nitrogen. So if I have 1 mole of hydrogen and 1 mole of nitrogen, then all I have to do is take this 1 mole, and I'm going to color code them to make it easier. All I have to do is take the 1 mole of hydrogen and divide it by its coefficient. So 1 divided by 3 is 0.33. So I can get 0.33 moles of ammonia. Well, I'll get more because I got to deal with the 2, but don't worry about that right now. But I'll get 0.33. Now, if I take the 1 mole of nitrogen and divide it by 1, 1 divided by 1 is 1. Okay, we are looking for the limiting reactant. That means we got to figure out the smallest number that I can make. So in this particular case, the question is, what's smaller between 0.33 and 1? And the answer is obviously 0.33 is smaller. That means this is my limiting reactant. And nitrogen is my excess. That's what that means. Okay, so now when I am doing my stoichiometry, so you have to do this step here. So what we just did, you have to do, this is step number 1 that we talked about right here. And then step number 2 is right here. So step number 1, step number 2, you have to do that. And once you do that, then you just go do your regular stoichiometry. So it is more work to do a limiting reactant problem, but then you just have to do those first 2 little steps and then you go. So if hydrogen gas is my limiting reactant, that means I use hydrogen gas's information. So you will use the known, I was going to say number of moles, but that you might not work out. So we're going to use the known for the limiting reactant to solve the problem. Well, goodness. Okay, so we can do that really, really quick. Now, I'm not going to take myself all the way back to knowing that I have 2 grams of hydrogen because I've already solved for the moles. So I've already done the first step of the stoichiometry here. I'm not going to redo it. If you want to start with the 2 grams of hydrogen, knock yourself out. But that's just wasting your time. So I'm going from 2 grams of hydrogen divided by its molar mass, so I have 1 mole of H2. That's my starting point. And I am going to go to, ultimately, I'm going to grams of ammonia. Well, my algebra dictates moles of H2 in the denominator. I'm at moles of H2, so if you're looking at the map, I am at like the blue colored circle, and I need to transition over to the red colored circle. So I've got to go from left to right. So that means I want to go to moles of ammonia, because I don't really care about the nitrogen anymore. I use my balanced chemical equation, and so hydrogen is a 3 and ammonia is a 2. So make sure you put them in the right spot, 2 and 3, times, cancel out that, times the next conversion factor. Moles of NH3 are here. I want to know grams, so that means I need to use the molar mass. And we already calculated that one, so it was 17.04, if I remember. All right, so with my math, it's going to be 17.04 times 2, and I'm going to divide it by 3. All right, so what does my calculator say? My calculator says 11.36. Let me cross out my like terms. I'm left with grams of ammonia. And that is not my final answer. And you should be able to recognize real quick that I haven't done my sig figs yet. So let's go take a look. Look back at your original known, which are in the problem. All right, so I have to use my smallest number of significant digits. So 28 grams of nitrogen is 2 sig figs, and 2 grams of hydrogen is 1 sig fig. So my answer, again, I'm back to having 1. That's fine. All right, let's see if you can remember how to round 1 sig fig with a number that is bigger than something that's in the ones place. All right, so with that being said, this is my 1 sig fig. I got to chop it off. Oh, I ran right through my 11. There. I have to chop it off. All right, look back 1 space. Does that 1 round the one in front of it up? And the answer is no, it does not. It just falls away. So I have a 1. But remember, this 1 in the front, the leading one, is in the tens place. This is the ones place. 11 does not round to 1. 11 rounds to 10. No decimal point. Grams of NH3. So, what is the difference? Because they look very, very similar. You have a regular stoichiometry problem over here on the left. You have 1 known. You have a stoichiometry problem with a limiting reactant. and you have two knowns, and sometimes it will tell you in the problem, like what is the limiting reactant or something like that, and that's a key that this is a limiting reactant problem. And sometimes they don't, they just give you two knowns. And so in the minute you see two knowns, you have to there's an extra step involved. Well, there's technically two steps, right? So first of all, you've got to make sure you have moles for each one. In this case, we had grams, so we had to go find the moles first. And then I had to do my little ratio. That's like figuring out my s'mores or my hamburgers or my hot dogs or dogs and cats. Figure out how many I can make. That's step 2. And then once I know who the limiting reactant is, I'm going to use that limiting reactant information from now on to solve the problem. Because the excess, the one that's extra and left over, I don't need it. If that information is not necessary for me to solve the problem. Because it's not going to dictate my final product. Okay, so that is limiting reactant problems. So hopefully now you can go and solve your problems 4 and 5. There was some other vocabulary that was on there that I'll go ahead and tell you right now. You're going to see something called theoretical yield, or I'm trying to think if they use a different terminology on your handout, but I don't think so. So here, theoretical yield, and then there's actual. Okay, so theoretical yield is what you get when you do stoichiometry. So every time you do a stoichiometry problem and you're calculating, that's theoretical yield. So the 10 grams of ammonia, that's my theoretical yield. Or up here on this other problem, the 30 grams of ammonia, that's my theoretical yield. That's how much ammonia I should get when I am making ammonia in this particular situation. So that's your stoichiometry. But if you've ever baked in the kitchen, and if you were making a cake or something like that, and it tells you you're going to get 24 cupcakes or something along those lines, lots of times you don't end up with actually 24 cupcakes because stuff happens. The batter sticks to the side of the bowl. You lose some. Some might fall out onto the counter or whatever. And so you don't actually necessarily get what you calculate or what you should get because stuff happens. Same thing in chemistry. Stuff sticks to the side of the container. It might boil over. Different things happen. And we usually do not get our theoretical yield. So our actual yield is what you get in lab. And it should be less. It should never be more. It should never be more than your theoretical yield. So actual yield should be less, and this number is going to be smaller because you will lose some. You should never get more than your theoretical yield. So if they ask you to calculate the percent yield, then all you're doing is you're taking your actual, which is your smaller number, divided by your theoretical, which is the stoichiometry calculation. Divide them and times them by 100, and that's your percent yield. So they might say, we actually got this much ammonia when we did this experiment. And then you could calculate the percent yield just by plugging it into that formula. It's not something that is, we do this calculation a good bit in chemistry, but it's not something that's heavily taught because they assume that you already know how to do percentages from math. So just to give you a heads up on that, I think the last question on your homework asks you to do that. So there you go. Thank you. Bye.